Hello, dear viewers. Thanks for taking out time to check out this exciting lecture on equilibrium of forces. In this lecture, we'll be talking about three important things, and they are equilibrium, resultant, and equilibrant. Now, these are three key terms in the topic equilibrium of forces. There are three key terms, important terms which must be understood as you study the topic equilibrium of forces. So we shall start with the first one, which is equilibrium. Then we move over to resultant, and we move over to equilibrant. So whenever you hear of the word equilibrium, what comes to mind? What does it mean? Now, equilibrium simply means a state of balance. It simply means a state of balance. That means whenever some physical quantities are acting on an object, what's the effect on that object? What's the effect that we observe on that object? That's what brings us to the concept of equilibrium. So, if I have an object like a stone or a ball, and that ball was static, let's assume this ball was just static in space, in the atmosphere. It was just static, it wasn't moving upwards, neither was it going downwards. Now, a force began to pull the ball upwards, or let's say a force attempted to pull the ball upwards. At the same time, another force which is equal to the one that attempted to pull it upwards was also trying to pull the ball downwards, which we can call F2. And at the same time, another force was also trying to pull the ball to the right, which we can call F3. And at the same time, another force was trying to pull the ball to the left, which we can call F4. So we see four forces in total acting on the ball. As a result of these four forces, eventually the ball doesn't move to any direction. And you wonder why. Why is the ball not moving to any direction? I thought forces were acting on the ball, so it should move to a particular direction. And you wonder why. I thought forces were acting on the ball, and so it should move to any of these directions, but it's not moving to any of the directions. The question is because there is a balance of forces. There is a balance of forces. While F1 tries to pull the ball upwards, the ball was about to go upwards, but F2 began to pull it downwards. That created a balance. Now F3 tried to pull the ball to the right, but F4 started pulling it to the left. That also created a balance, and so the ball doesn't move to any direction. We therefore say that there is a balance of forces. Another word for that balance is equilibrium. As I've just said, equilibrium simply means a state of balance. That means I can say that there is an equilibrium of forces here. There is an equilibrium of forces. So in short, that's what the term or the word equilibrium means. So there can be equilibrium for any given quantity as long as we can observe it. Yes, any observable quantity, any quantity that is capable of being measured or being observed, equilibrium can occur for such a quantity. There could be equilibrium of time, equilibrium of forces, equilibrium of speed. Now, we say that an object is in equilibrium when there is no change on the body despite the action of some quantities. There is no change of the body despite the action of some quantities. Say for example force, as I've just illustrated with this example. Despite the action of four forces on the ball, there is no change in the position of the ball. The ball remains static, it remains in that position. So we say that the ball is in equilibrium, it's in an equilibrium state. Now, to further explain the concept of equilibrium, I'm going to draw a diagram to explain further the concept of equilibrium, how it relates to other quantities such as flow rates. Now, when we come over to motion of fluids, which can be referred to as fluid mechanics, we talk about flow rates. Now, we have a drum. Which contains a particular which contains we have a drum which contains a particular kind of liquid, let's say water, and that drum has a tap. So that drum has a tap which can be opened. So the drum has a tap, and the tap can be opened or closed, and there is a pipe connected. There's a pipe connected into the drum, through which water can also come into the drum, and then of course water can exit the drum from this place. Now, this drum being filled with water or having a level of water content in it, let's assume the drum has a level of water content that's up to this point. Now let's look at the flow rate of water. Let's look at the flow rate of water out of the drum and into the drum. Now, if the rate at which water leaves the drum, is equal to the rate at which water enters the drum, then we say that there is an equilibrium of flow rate, because this drum will never become empty despite the fact that the tap is open and water is actually flowing out. Yet the drum won't get empty, it won't become empty, because there is an equal rate of water flowing in. Water is flowing in at an equal rate to which it's going out. So we say that there is an equilibrium of flow rate. Okay, so that's the basic concept of equilibrium. And in physics, there are three types of equilibrium. We have dynamic or kinetic equilibrium, and we have the static equilibrium, and there is thermal equilibrium. So dynamic equilibrium simply talks about when this balance occurs for objects in motion. At what point do we say that there is an equilibrium for an object which is in motion? Now let's take a look at an object falling down in a fluid. Now, if you have a stone which was dropped into a fluid, and the stone had to fall down into the fluid with a particular speed or a particular velocity. Now you see that the factor influencing the speed of the of the ball in the fluid will be the weight of the ball, which is a function of gravity. That is the mass of the ball times gravity. That's what makes up the weight of the ball. Now, the weight of the ball makes the ball fall down into the fluid, or travels down into the fluid. But there are friction in the fluid, and that friction is called viscosity. That friction is called viscosity, and it resists the motion of the ball in the fluid. It resists the motion of the ball in the fluid. Now, viscosity is a form of friction that we find in fluid. Fluid. Now, the word fluid simply means anything not solid. It could be liquid or gas. So anything not solid, which is a liquid or a gas, is referred to as a fluid. So just to note that. Now, there is also another force which is known as the upthrust. The upthrust is also a force that acts in the opposite direction to the direction of the weight of the body. Upthrust. You see, now while the weight of the body is making the stone go down into the water, viscosity and upthrust wants the body to remain balanced, doesn't want the body to move downwards, so it's opposing the motion of the body downwards. Now, the body will still move downwards anyway, that is, the stone will still go downwards anyway, but a point will be attained in the motion of the stone downwards in the fluid. The stone will come to a point where the weight of the ball balances with the sum of the viscous force and the upthrust. Upthrust is also a force. Yes. So a time will come where the weight of the ball will be balanced with the sum of the viscous force and the upthrust force. So at this point, the stone begins to move. The stone will still be in motion, but it begins to move with a uniform velocity. That means it can no longer accelerate in the fluid. So the stone does not accelerate anymore as it's traveling downward in the fluid. It's no longer accelerating, so it has attained a uniform velocity. Now, this uniform velocity is what we refer to as terminal velocity. That's what we refer to as terminal velocity. Terminal velocity. So whenever a body is falling or moving in a fluid, and then there is a balance of forces, and the body no longer accelerates, so we say that the body has attained terminal velocity. This occurs also when raindrops descend from the upper atmosphere down to the earth. The raindrops attain terminal velocity before landing on the earth. So it's actually not accelerating anymore, but it's having a uniform velocity. So we say that the raindrops, or the motion of the stone moving in the liquid, is actually in a state of equilibrium. It's already in a state of equilibrium. Since the forces are balanced, we can call it equilibrium of what? Of the forces acting on the stone as it's moving downward in the fluid. So we say that the stone is at a state of equilibrium or balance, though in motion. So we refer to as this kind of equilibrium, we refer to it as what? Dynamic equilibrium. Dynamic equilibrium. Now, what of the other case when the body was actually static before some forces started acting on the body, like I explained in this diagram, which you can see right now, the diagram of the ball pictured in space and four forces acting on it. That this type of equilibrium is what we refer to as static equilibrium, because the body is in equilibrium and yet it's not moving. Or even if the ball was in motion, even if it was in motion, originally before the forces began to act. Maybe it was moving upwards with a speed of the speed of maybe it was moving upward with the speed of 0.2 meter per second before another force began to pull it downwards, and then also sideways. Eventually the ball stopped moving and it became fixed at a point. So we say that body is in static equilibrium because it's not in motion. Hope that's clear. Then when we talk about thermal equilibrium has to do with heat, equilibrium of heat flow. Heat is a form of energy and it can flow from one object to the other. It can flow from one space to the other, from one point to the other. So when there is an equilibrium of heat flow, we say there's thermal equilibrium. All right, now we are done with the term equilibrium. Now let's move on to the term resultant. When we talk about resultant is a special word is a special word, and it's a special word because it means combination. It also means combined effect. Yes, just like two in one. That's what resultant actually means. So to explain properly the word resultant, I'll draw a diagram. If we have we have a stone, using a stone once again, we have a stone, and then there is a force acting to this direction on the stone and another is acting to this direction on the stone. So we have F1 and F2. Now the forces acting on the stone attempts to move the stone to a particular direction. Now the question is, to what direction will this stone move? Is it going to move to this direction, or will it move to this direction, So what direction will the stone move? That's what we that's what resultant tries to explain, or that's what resultant means. That's what resultant talks about. So what's the combined effect as a result of these two forces? While F2 tries to pull the body to the right, F1 tries to pull it to the left at an angle upwards. So eventually you find out that the ball will have to move to this direction. Yes, so because the ball is trying to go right, and while it's trying to go to the right, F1 is also trying to pull it to the left but upwards. So eventually it takes its direction this way and then it begins to go upwards like that. So you see, so we call this force the resultant force. That's the resultant force. We can define the resultant of a force as that single force which acts alone. That is, when it's acting alone, it will have the same effect in magnitude. Magnitude means size. It will have the same effect in magnitude and direction as two or more forces acting together. So when two or more forces are acting together, as illustrated here with F1 and F2, the single force that we can use to represent the effect of all these forces acting on that body, because they're acting together. So while they're acting together, what's the single effect that is produced? And it's usually seen, the effect is usually seen in size, magnitude, and direction. Yes, size means that the object will move with a magnitude of a force. Since we are talking about forces now, so the object being acted upon by several forces, the object itself will not have a given force that moves it in a particular direction. Now that force is referred to as that force, whatever the value is it 50 newton or 20 newton, that size is what we refer to as the magnitude. That magnitude came as a result of these two or more forces acting on that object. That magnitude or that size came as a result of these two or three forces or more acting on that object. If they were not acting on the object, that magnitude, that particular size will not result. Or if it was only if it was just the F2 that was acting on the object, we won't be having a magnitude of arrow here going to this direction. No, the magnitude of the force acting on the object will just be the value of that force acting to that direction, to the right. But now that a force is acting to the right and another is acting to the left, there is going to be a combined effect producing a new magnitude, a new size of force that will not take the body to that specific direction, which is also as a result of the directions of the two forces acting on the object. So that's the concept of resultant. Resultant, as the word implies, resultant, the result of. So you can use that to remember the definition of resultant. And then lastly, we'll talk about talking about equilibrant. Equilibrant. Whenever you hear the word equilibrant, equilibrant simply means the balancing force. The balancing force. That's what equilibrant means, the balancing force. Now, when these are two forces, F1 and F2, act on the ball, the ball will have to move to the direction of the resultant, which is upwards like this. But what if we want the body to be in equilibrium? We don't want it to move. We want the body to be in equilibrium. That means I have to know the value of this resultant, and then I have to apply the same value of the resultant to this direction. Yes. So while applying the value of this resultant to this direction, the body stays balanced. The body stays in equilibrium. It doesn't move to any direction anymore because the forces have been balanced. So this force which I have just applied to the opposite direction of the resultant is what we refer to as the word equilibrant. Equilibrant. Therefore, we can define the equilibrant of two or more forces as that single force which will balance all the other forces when they are acting together on the object. When they are acting together or taking together on the object, yes, when they're acting together on the object, that single force that will balance the effect of those forces is what we refer to as the equilibrant. Now, we can say that the equilibrant is always opposite in direction to the resultant, since it's meant to balance the forces and to oppose its consequent motion or its resultant motion or its resultant direction. It's meant to oppose the motion of that object to the direction that results as a result of these two or more forces acting on the object. So we call that the equilibrant. It's acting opposite direction. So if we're having this like a pulley or a pivot that can rotate, and then there is a force this way, and there's a mass hung here. And then there's also a mass hung here, and there's also a mass hung here. Now, this mass has a weight pulling it downwards, and these masses too also have weight pulling it downward. So let's call this M1, M2, and M3. Now, when M3 is moving downward, you can see M3 is suspended by these strings. M3 is suspended by these strings. Yes, it's suspended by these strings. And these strings are connected to these masses which we have over here, because this is like a roller or a pivot that can allow sliding motion of the strings on the roller. So now these masses can actually move downwards, and when it's moving downward, this mass should be going upwards. But in this condition, there is there was an equilibrium. We observed that there was an equilibrium. Why would there be an equilibrium? There will be an equilibrium when the forces acting on this mass now, the forces acting on this mass are this force going upwards, this force going upwards, and then yes, that's the force in this system now. The force in this system, yes, because this string, the tension in the string which acts to this direction, and then the tension in this string which acts to this direction, and then the weight of this mass causing a force in this direction. M2 and M1 M2 and M1 are the causes of this tension in the string. So they are seen in those forces. So we can say that the diagram of the forces in this system is just this. That's the diagram. A force acting in this direction, a force in this direction, and the weight in this direction. Now for there to be equilibrium such that there is no motion in the system, it means that the force of let's call this force F1, let's call this force let's call this F1, F2, and F3. For there to be balance in the system, that means no motion. It means F1, F2, and F3 must be in equilibrium. F1, F2, and F3 must be in equilibrium. So the first thing we are going to ask ourselves is, what is the combined effect of the forces? What's the combined effect of these two forces F1 and F2 on the mass F3? The combined effect of those two forces will actually move in a direction like this. Yes, because F1 tries to take it this way and it's upwards, and F2 tries to take it this way and it's upwards. Eventually the mass will not actually go in any of those two directions, but it will not take a direction that has to go upwards. Yes, that is why we call it the combined effect or the resultant. So this becomes the resultant. So the body has to now move upward, because while it's trying to go to this direction, this other force says no, come here, and eventually it will find itself just going upwards like this. That's the resultant. And that is why if these two masses are large enough, greater than this mass M3, while these masses are going downwards, they'll be causing a force on this mass M3. They'll be causing a force on this mass M3, which we have seen here, going this direction and going this direction, and eventually mass M3 begins to go upwards. That's the resultant. Now for there to be equilibrium, it means that the weight of M3 must be equal to this resultant. The weight of M3 is the mass, that's M3 times gravity. M3 times gravity has to be equal to this resultant, which is going upwards. Yes, when that happens, then we can say that this force which is going downward has balanced these two forces which are actually going upwards, and then there is equilibrium in the system. So we call this force the equilibrant. We'll call it the equilibrant, and then these are the regular two forces that were acting on the object, but this force is the equilibrant. And then the resultant is that force which will move upwards, that is the opposite of the equilibrant. And how do you show opposite? Whenever we're talking about forces, we show opposite by changing the sign. So if the force of the equilibrant was, let's say, 20 newton, the resultant becomes minus 20 Newton. So that tells us that the resultant is the same, is of the same size as the equilibrant, but is going to the opposite direction of the equilibrant. So it's going to the opposite what direction. So that's the concept of equilibrium, resultant, and equilibrium. They're actually interesting terms which you can understand by just observation, and that's the idea of equilibrium of forces. You have to do a lot of observation, you have to think and just try to picture objects in motion due to the action of several forces on the object. You just try to picture, oh, what direction should this object move as a result of what direction should this object move in as a result of these two forces acting on that object right now. And then you get the resultant, and then you get the equilibrant if you are asked to do so. And then one other important term in the concept of equilibrium of forces, or what we call resolution of vectors, equilibrium of forces or vectors. That term is called resolution, vector resolution or forces resolution. Because when two or more forces begin to act on an object, you have to get the resultant, and while trying to get the resultant, you are actually doing what is called resolution of forces. Resolution. Now, the concept of equilibrium, equilibrant, and resultant finds application in the topic equilibrium of forces. You have to watch out for further videos that these that addresses the aspect of solutions to problems on equilibrium of forces. You have to watch out for those videos, and subscribe to the channel. And as well, if you like the video, just click on the like button, then subscribe to the channel, and also click on the bell icon. Click on the bell icon so that you can get notifications. Just click on the bell icon so that you can get notifications whenever new videos are uploaded to this channel. And bye bye. And remember that Jesus loves you and is coming very soon. God bless you.